Circles. Today's session is about circles. So what is a circle? How do we define circle in general sense? We have seen many objects in real life which define a circle. Say for example, I have a shape of this stapler, of this sellotape, which looks in circular shape. So this kind of a shape which we see in real life is a circle. This board is not a circle because it is not circular. So by seeing the shape, we can identify whether it is a circle or not a circle. In this case, the rim is a circle, but the face, the width face is not a circle. Similarly, I have a disc which has many different circles as can be identified. One of the outer circle is this because it is circular in shape. The other circle is the rim out here, and there's one more inner circle. So these are the different sizes of the circles which are identified in the disc. The bigger circle, the next bigger circle, and the smaller circle. So circles can be of different shape, but anything which represents the shape of being round is called a circle. There are many examples in real life which can be taken along with the two example models which you have considered. Like you can take the clock, the wall clock usually comes out the circle. Introduction. Of the circle. Imagine I have a wall clock where my second's hand moves in this direction. It goes on and etc. So this second's hand which moves in this clockwise direction in the wall clock tries to make, retain back here, tries to make a circular motion. So the motion made by the tip of the second's hand in the wall clock is called circular motion. So a circle is something which is formed when any object rotates round its fixed point. So any object which rotates on fixed point tries to make the outer margin which looks like a circle. Is how we define in the general sense of understanding a circle. The currency coin, a 1 rupee coin, a 5 rupees coin, a 10 rupee coin, etc. are all circular in shape. So they are all circular in shapes. Is how we understand a circle in real life model. This is a circle, this is a circle, this is a circle, and this is a circle. For example, I take a photo frame which defines a lady out here. This is not a circle. because you take the fixed point and move the side, it does not form a circular shape. Any fixed point and then move, it does not form a fixed shape. So any object when taken with a fixed point and then rotated around its rim, the kind of a shape we get is called a circular shape. So a circle is something which has fixed point and moves at constant distance throughout in all directions, just like the seconds hand of a wall clock. To take an example of circle, 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 not a circle, is how we understand the concept of a circle. Circle in mathematics. Now that we have discussed about what a circle is, like how does a circle look like, what is its shape, now that we can recognize a shape to be a circle or not a circle, now comes the question, how do we draw a perfect circle? When I draw by free hand, it is not that easy that I get a full circle. For example, when I just draw, I may move out and I get a kind of a circle which is not perfect. So I don't get a perfect circle. So my question here is it perfect? No, it isn't. So how to draw a perfect circle on a sheet, on a rough sheet, is the concept which you're going to see in this session. Construction of a circle is today's session. Construction of a perfect circle. So let's see a perfect circle in its construction. When I take a fixed point, let me take a compass from the geometrical instruments. We all are aware of a compass. So we took the pencil and just put the point of the compass out here and move with certain radius or with certain distance and try to move the pencil out here. So I get a kind of a shape which looks like this. So I get a shape which looks like this with the fixed point of the compass. So the kind of shape I get when I take the fixed compass and move the pencil round throughout the page is what a perfect circle is. A perfect circle is obtained by using the compass. So here the compass gives me a circle derived from a compass. A circle derived from a compass. And this is no doubt a perfect circle. This is perfect. Circle is how we conclude. So any circle which is derived from a compass gives me a perfect circle. So for a construction of a circle which needs to be perfect, we use the compass and then draw it around the page and we get a circle of this type. This is not a perfect circle because it's drawn by freehand, but this would be a perfect circle if you can join through the compass. It's how we understand constructing a circle with and without compass. Now that we have seen the circle and its shape and the construction methods of constructing a perfect circle, now comes in understanding the mathematical definition of a circle. Mathematically, we need to understand what a circle is. So this session is about investigating the mathematical definition of a circle. So let's see how we define a circle in mathematics. Mathematical definition. Let's come back with the construction of a circle using compass. As we have discussed in the previous session, that a perfect circle is obtained when we derive through a compass. So we have taken the compass fixed at here, and when I take the rotating, I get a circle in this manner with a fixed point out here. Is how we understood a circle. So how do we define mathematically this fixed point which derives a perfect circle? Well, when I move the compass with the fixed point fixed out here, and at half the way I move it here, do we get a perfect circle? So my question here is, can we get a perfect circle if this fixed point is moved in midway when we derive the circle with the compass? No, we cannot. One can investigate using a compass to move the compass out there, the pointer out there, and then try to complete the circle. In the halfway, we cannot get a circle. A perfect circle is obtained only when the pointer of the compass is fixed exactly at one particular point, no moving aside. So this makes us clearly understand that for deriving a perfect circle, this must be a fixed point. The pointer must be at a fixed point, is how we understand the first investigation of a circle derived from the pointer, is how we understand through this. Now, as we see clearly that as the pointer with the pencil which moves out here derives a perfect circle, I clearly see that whenever I derive a perfect circle through the compass and measure the distance between this fixed point and this corner off with the ruler, I get same distance. That is, the distance I measure here and the distance I measure here, or the distance I measure the other side, throughout the circle, I see that all the distances I measure will be at equal distances. Taken with the ruler, the measuring of the distance wo from A, wo from B, wo from C, and wo from D, wo from E and F, etc. gives me the same distance. The distance will not differ at any corner of the point taken on the circle and measured with the distance from the fixed point in the center. So we have many mathematical properties which arise through the circle. We have many mathematical properties which come into existence through this investigation outcome. So what are the different things we see here? For a perfect circle, the first point is that center wo must be fixed. Center wo must be fixed. And secondly, the center must be at equal distances from any point on the circle. The second point is that center wo must be at equal distances from any point on the circle. So this is how we define the perfect circle. For a perfect circle, the center O must be fixed. The fixed pointer of the compass must be fixed at that point when you draw the complete circle. You cannot move it in midway. Is how I understand the center O must always be fixed. Secondly, the center O must be at equal distances from any point on the circle. So when I take a ruler and measure the distance OA, OB, OC, OD, OE and OF, etc., all the distances must be same. Even if one distance is not the same as other distances, then the circle is not perfect. It is not a circle. Mathematically, a circle has two basic properties: center fixed and center at equal distances from the points on the circle. It's how we understand the circle derived from these two basic properties. The mathematical definition of a circle. Now that we have defined circle in the mathematical sense, now comes what are the key factors involved in a circle. Like every solid figure every figure which we have been discussing exclusively, like triangle, a parallelogram or other objects which are discussed in the previous session, had their own basic understanding of the structures through the sides, angles, vertices, areas, etc. Similarly, a circle is also examined for similar kind of properties in understanding the structure of a circle. Key factors involved with the circle. Key factors involved in the circle. So what are the key factors involved in the circle? So let's take a circle and understand the key factors. More importantly, identifying the key factors in a circle. So here is the circle which is obtained through the pointer of the compass. So this pointer makes me understand that this is the center of the circle. So the fixed point from where the circle is derived is called center of the circle. So here comes center of the circle. So this point is called the center of the circle. Next comes the fixed distance. Now the second property we have identified in the mathematical definition is that this point is at equal distances from any point on the circle. So what is that equal distance called? The center is denoted by O or C, or generally I denote the center with C and my point on the end to be denoted by some P. So P is a point such that here the distance from center to one of the points of the circle is P. So what is CP called? Initially, the fixed point denoted by C is called center of circle. The fixed point C is called center of circle, and the distance from center to any point, that is the fixed distance, CP, is called radius of circle. So this is given by the special name called radius of the circle, as it defines the radius, the curvature. Therefore, the distance CP is called radius of the circle. So circle has two important key factors. One is the center, one is the radius. The fixed point being the center of circle and the fixed distance being radius of circle. Radius and center for the circle with fixed distance and derived circle is how we understand the key factors involved with a circle. Now that we have discussed about the center and the radius, now comes the question on how we can connect the center and radius, or how we can define the radius in different ways of understanding radius. So here the session is about understanding the radius. So radius, as we see, is the fixed distance from the center to any point on the circle. That is, when I take a circle and when I take the center, this distance is called radius. CP, the distance CP is called radius, but sometimes radius is also represented by the line segment CP. So radius is generally denoted by small r. So when I represent the radius, I represent with r. Is how we define the radius. So radius denoted by r. And it's very important to note that radius is represented in both ways. Sometimes it is represented with line segment CP, which is r, and sometimes it is represented by length CP, which is r. So the two ways of representing radius, one is through the line segment CP, which is r, and one is through the length, which is mod CP, which is equal to r. But both mean the same, and radius is generally denoted by r. Is how we understand the radius connected with understanding the radius. And the most important understanding is, say for example, I take a circle and a circle. So what is the difference I identify between each of the circles? How do we identify these three circles? Clearly, I see that the radius of each of the circles is different. How different? What is the relation between radius of this and this and this? So let me take the radius of the first circle is r1, the radius of the second circle is r2, and the radius of the third circle is r3. Then how do I connect the radius of r1, r2 and r3 is the biggest question out here. Clearly I can see that this is r1, which is smaller than r2. So I see here r1, which is smaller than the next radius, which is r2, and this is more smaller than r3. That is, the highest radius is this and the smallest radius is this. This is how it comes in ascending order. So the radius of the first circle R1 is less than radius of the second circle, which is R2, less than radius of the third circle, which is R3. Therefore, I clearly understand that as the value of the radius increases, as the length of the radius increases, the circle becomes bigger and bigger. So finally, we conclude that the radius of the circle decides the size of the circle. Very simple. The radius being small, the size of the circle is small. The radius of the circle being bigger, the size of the circle is also very big. Is how we understand the radius connected with the circle. Here I have a disk. The radius of this bigger circle is bigger, and the radius of this circle is smaller than the radius of the previous circle, and the radius of this circle is smaller than the radius of the outer circle. The radius of the smaller circle is the smallest, the radius of the bigger circle is the biggest. Is how we connect this with understanding the radius of three circles. So my learning outcome here is the radius of the circle decides the size of that circle. So here my learning outcome comes out to be that the radius of the circle decides the size of that circle. Smaller the radius, smaller the circle. Bigger the radius, bigger the circle. The size of a sun or the size of an earth, which are circular in shape, or the size of a moon, are decided by their radii, by the radius of the earth, the moon, the sun, etc. Radii is plural form of radius. Is how we connect the radius with the circle. Understanding the radius of the circle through its size. Now that we have discussed about the key factors involved with the circle, now comes the understanding of a circle in a planar region. Today's session is about a circle in a plane. So let's see how a circle divides the plane into different regions. Circle in a plane. So a circle in a plane. So let's take this plane of the marker board. So on this whiteboard, I have a circle in this planar region. So in this planar region of the white marker board, a circle, it divides it into two regions. This is the region inside and this is the region outside. So a planar region with a circle makes it with two regions. One is which is called interior region because it is inside the circle, and this which is called exterior region because it is outside the circle. So for a circle divides the plane into two regions. One is interior and one is exterior. So I come to the conclusion. A circle divides the plane into two regions. A circle divides the plane into two regions. One is interior region and the other is exterior region. Interior and exterior region. The region inside the circle refers to the interior region. And the region outside the circle refers to the exterior region. That's how we understand the interior region and the exterior region in the circle. A circle divides the plane into two regions. Interior region denoted by this and exterior region as referred in the entire plane of the marker board. It's how we understand the regions inside the circle and outside the circle connected with a circle. Now that we have defined the interior and exterior region when a circle divides the plane into two regions, let's understand what a circular region is defined in the branch of mathematics. Circular region and its definition. So what is a circular region? Let's recap with the interior and exterior regions as discussed in the previous session. Now I have a circle on this white marker board. Then I have understood the region inside, which is interior region, and the region outside, which is exterior region, are the two regions out here. Now, here is the circle as denoted by the round rim. So what is the circular region in this? So here, the circular region is defined in mathematics to be all the interior region, which is denoted by this, including the circle. So circular region in mathematics is defined to be the interior region including the circle, but all the exterior region is not taken into account. So circular region is interior region plus circle is how we understand the circular region connected with the circle. Circular region equals interior region as represented by the dotted plot and the circle, but not the exterior region. This equals interior region plus circle. It's how we understand the contrast between interior region, exterior region, and the circular region. Now that we have discussed about circle and its various properties, most importantly, how a perfect circle can be constructed on a plane. The regions, the different regions which define a circle, the interior region, exterior region, and the circular region. Now comes the discussion of further properties of a circle. Today's session is about chord of a circle. So let's see what chord of a circle is in today's session. Chord. What is a chord? So let's see the definition in brief for a chord of a circle. For this, let's draw a circle. Imagine I have a circle in which I would like to define a chord. So here, the chord is defined for a circle to be the line segment which joins any 2 points in the circle. So here I have a circle for which I take 2 line segments. I have to take 2 points which make the line segment on the circle. For example, I take a point here on the circle and I take another point out here on the circle. Now, this point on the circle is denoted by A and this point on the circle is denoted by B. So for these 2 points A and B on the circle, a chord is defined as the line segment joining any 2 points. In this case, joining the points A and B. So let's join the points A and B for this circle. So here I have a line segment which joins any 2 points on the AB. So this line is called the chord. Is how we define a chord. A chord is defined as the line segment which is formed by joining any 2 points on the circle. Is how we define a chord. A chord is a line which cuts the circle. Is how I understand geometrically. The definition out here in words is that a chord is a line segment which joins any 2 points on the circle. So a chord is a line segment which joins any 2 points on the circle. In this case, the 2 points A and B are joined to form a line for the circle, and this line AB is called the chord. So in this diagram, line segment AB is the chord. Is how I understand the definition of the chord. A chord is a line segment which joins any 2 points on the circle. In this case, AB being the chord. Is how I understand a chord connected with the circle. Now that we have defined a chord, let's see in the session continued how many possible chords can I draw for a circle. With the definition of the chord is followed by the number of chords investigated for a circle. So this session is about chord with possible number of chords for a circle. Is what we're going to see in the session. So now that we are defining about, we are investigating the possible number of chords for a circle, let's take a circle and investigate with joining of 2 points, because a chord is defined itself when we join any 2 points of the circle. The line segment which is obtained by joining any 2 points in the circle is a chord, is the definition itself which we are going to investigate with various points taken on the circle. So let's take a circle and various points on the circle. So here is the circle which defines. Now for this chord, for this circle, let me take 2 points out here. So I denote this point with A1 and I denote this point with B1. So this chord is obtained when I join the points A1 and B1 on the circle. So A1 is a point on the circle and B1 is a point on the circle which is joined. So the line segment A1 B1 defines a chord. Defines one of the chord. Now let's take possible number of other set of points. I take a point and then join with other point on the circle and say this point is referred on the circle with A2 and this point on the circle is referred with B2. So I have another line which is formed, the line segment which is formed when I join the points A2 on the circle with B2 on the circle. So this is one more line segment. Therefore, by going with the definition of the chord, I can say proudly that A2 B2 also is a chord because this line is obtained when I join 2 points on the circle. A line segment which is obtained when joining 2 points on the circle is a chord, and hence A2 B2 is a chord. Is also a chord. Let's investigate with one more set of points taken on the circle. So let me take a different set of, here I take a point and here I take a point. And then I join the 2 points. So I take these two and I join so that I get this point on the circle is denoted by A3 and say this point on the circle is denoted by P3. Now clearly this also forms a chord because this line segment is obtained by joining the 2 points on the circle and hence by definition is a chord. Therefore, A3 B3 is also a chord. So by this time of investigation, what do we conclude? We conclude that we have different sets of chords formed by different points on the circle. Therefore, as we have infinitely many points on the circle, therefore the infinitely many points equally join to form infinite number of chords. Since a circle has infinite number of points, there will be infinite number of pairs of points which can be joined to form infinitely many line segments and hence infinitely many chords. Here's how we understand the number of chords in the circle. So we have here, since a circle has infinitely many points, therefore infinitely many line segments are possible. Many line segments are possible, joining the pair of points for each infinite points, each pair joined with each other. Therefore, since a circle has infinitely many points, therefore infinitely many line segments are possible in the circle. Therefore, that is, a circle has infinitely many chords. So we conclude that since infinitely many line segments are possible through infinitely many pair of points on the circle, therefore all those lines by definition of chord, form the chords for the circle. Therefore, a circle has infinitely many chords. Chords is how I understand a circle and its chord. A circle has infinitely countless number of chords is how I understand through the session's investigation. Now that we have discussed about a chord of a circle, now comes the most important concept used in circles connected with chords. Diameter is what we're going to discuss in today's session. Diameter of a circle. So what is a diameter? Now that we have discussed about a chord being defined as a line segment which joins any 2 points on the circle, similarly a diameter has its own definition. So let's see how a diameter is defined and how we connect the chord with the diameter. To start with, the definition of the diameter. So in order that I define a diameter for a circle, let me take a circle into consideration. So here is the circle out here. Now this circle has the center. As we know that every circle is derived from the fixed point which is the center. So this circle also has the center. Say my center out here is this dot. Now let me just take the definition before I understand the diameter. So here comes the definition of the diameter. A diameter of a circle is the line segment which passes through the center of the circle. Now here we have many line segments which pass through the circle, but there's only one fixed line which passes through the center. So here any line which passes through the center is called diameter. Suppose I have a line AB which passes through the center, then I call this line AB as diameter. AB is the diameter. So in this diagram, since AB passes through the center of the circle, since AB passes through the center of the circle, therefore AB is the diameter, is how we conclude the diameter of the circle. So in this diagram, this is the diameter. Diameter of a circle is AB, and its definition is given out here. So we finally conclude that a diameter of a circle is the line segment which passes through the center of the circle. So here this is the diameter because this passes through the center. If I take a line AB which does not pass through the center, then this line is not a diameter, but this line is a diameter because it passes through the center of the circle. Is how we understand diameter of a circle connected with a circle. Now that we have defined a diameter connected with the circle, now comes the concept of how we connect a diameter with the chord. How do we understand diameter through the chord definition as we have taken in the previous session? So this session is about connecting diameter with the chord of the circle. Diameter versus chord. So in order that we understand diameter in terms of the chord, let's revisit the chord definition. So chord is defined. A chord is defined as the line segment which joins any 2 points of the circle. Is how we understood the chord. That is, when I take this in terms of understanding through the diagram, I have this to be a chord Suppose I take the points A and B. This is a chord. Is how we understand. The line joining any 2 points of the circle is a chord. Then what is diameter and how is it connected to the chord is clearly understood through this definition, because when we say diameter, diameter is a line which passes through center of circle. So if I connect any 2 points in such a manner that it passes through center, then I can say that a line segment or a chord which passes through the center is the diameter, because a chord is nothing but defined even for a diameter. So if I take the line segment P and Q passing through the center, then clearly I can say that PQ is a special chord for the circle and PQ is given by the name diameter, because any line which passes through the center of the circle is a diameter, and hence the special chord PQ passing through the center must be the diameter for the circle. So here I understand that AB is the chord but cannot be the diameter, because this line AB does not pass through center, but the line PQ is the diameter. Is the diameter because it passes through the center. Simply, since it passes through center is how we understand the chord connected with diameter, or a diameter connected with the chord. And importantly, we have to understand that if I take the length of this chord and the length of this chord, we clearly understand that the diameter, which is also a chord, will be the maximum length. So length of the diameter will be maximum. it is the highest chord in the circle, also is one way I can connect with. So here I make the learning outcome that diameter, which is nothing but a chord, is the longest chord in the circle. So AB, PQ are the chords in which PQ is the longest chord because it is a diameter passing through the center. So my learning outcome here is that diameter is the longest chord in the circle, is how we understand the relation between a diameter and a chord. Diameter derived from a chord passing through center of circle. Now that we have related chord and the diameter for the circle, where diameter is nothing but a chord derived with a special case of passing through center. Now comes the discussion of how many possible diameters we can draw for the circle. Today's session is about the possible number of diameters which can exist in a circle, investigating the number of diameters in a circle. Possible number of diameters in a circle. So let's see with a circle taken into consideration and investigate on the possible number of diameters in the circle. I have a circle. Now let's say the center of this circle is here. Now as we know that diameter is a chord passing through center of circle, therefore let's take the different possible chords which pass through the center from various different directions of the circle. So if I start from this direction, I have a chord A1, B1 with a point A1 out here and a point B1 out here in the circle. Similarly, let me take another chord passing through the center in some other direction. So here I have A2 and B2. So here I have a point A2 which is taken on the circle and the point B2 taken on the circle in such a manner that all these three are collinear. Let me take one more in some other direction. I take here So here I have another line passing through this center. So this is A3 and B3. So here is different set of lines taken into consideration, but interestingly all three lines are passing through the center of the circle. That means all the three lines as drawn here, the dotted lines, are the diameters for the circle by definition of diameter. Therefore, initially I take A1, B1, which is a chord, a special chord, and hence is the diameter. Similarly, I take another line A2, B2 out here. which is a diameter. And similarly, I have the third one, which is A3, B3. So as I see here, since there are infinitely many points on the circle, I have infinitely many pairs of lines which I can make passing through center. So therefore, for infinitely many points in the circle, I have infinitely many diameters coming into existence. So my learning outcome here is that for any circle I take into consideration, the possible number of diameters in the circle are infinitely many. So therefore, there are infinitely many diameters in the circle. So coming to this, I can just draw the conclusion that since a circle has infinitely many points, since a circle has infinitely many points, therefore there exists infinitely many lines passing through the center of circle. Therefore, I conclude that since there are infinitely many lines which pass through center of circle, therefore a circle has infinitely many diameters. So this is the conclusion we make in case of number of diameters. My learning outcome, a circle has infinitely many diameters, is what we come into investigation of diameters of a circle.